let me start that. Okay. So during, I will try to fix the first part. So during the collision, we are imagining that there are these internal forces of M1 on M2, the force with which mass M1 pushes on mass M2. And of course, due to action sort of every action has equal and opposite reaction thing. The force of M2 on M1 is going to be minus of F internal. If M1 pushes on M2 with F internal, M2 pushes on M1 with minus F internal, okay? This is the internal reaction force or the interaction force or the collision force. You can call it whatever you want. So that's the free body diagram during the collision. We are ignoring for a moment that there are these potentially external forces like gravity and so on. Okay, this is the free body diagram. So we can apply impulse momentum relationship or F equals ma for each mass. Like here, we applied the impulse momentum relationship for the two masses put together. And for the two masses put together, total final momentum equals total initial momentum. But for the individual masses, what's going on, right? For the individual masses, sort of already by the premise of the problem or premise of the situation, the mass M2 basically goes from V2 initial to V2 final, right? So before the collision, this is the velocity. After the collision, this is the velocity. And then it goes from this velocity to this velocity in time delta t, which basically goes to 0 because we have infinitesimal time duration, okay? So this velocity change typically is non-zero, right? In other words, the object does change velocity, because if the object didn't change velocity, we wouldn't call it a collision. If the objects just start with some velocity and ended up with the same velocity, well, nothing happened, right? So usually when we say collision, something happened where the velocity is changed. So the velocity difference is non-zero. And remarkably, this velocity difference happened during delta t, this very small duration. So during the delta t, when the two objects are in contact with each other, you can sort of define this quantity, which is the average acceleration of, say, mass m2, which is final velocity minus initial velocity divided by time taken, okay? So final velocity minus initial velocity divided by time duration is the average acceleration or the mean acceleration. And so the numerator is just some number or some vector. It's going to be not necessarily 0 as we described. And the denominator is going to 0 because, well, the duration is going to 0. So the numerator, some finite number divided by denominator, which is going to 0, means that the acceleration of this object is basically infinity over that very, very short period of time, right? Basically, you have a finite change in velocity in infinitesimal time, and that means that your acceleration has to be infinity, right? Because acceleration is the rate of change of velocity. If you can change velocity instantaneously, what happened during that instant is infinite acceleration, because that's the only way to change velocity. Like if it was just a finite acceleration, then the finite acceleration integrated over a short period of time will basically be 0, or 0 time will be 0. Okay, so the acceleration is infinity for each object. For M2, we just established M1 basically has an acceleration as well, which is also going to infinity, assuming that delta t goes to 0. If the acceleration goes to infinity, well, because force is just mass times acceleration, and the only force or only, well, force that we can not ignore is this internal force. This internal force basically equals to mass times acceleration. You can add like mg and drag and so on as well, but all those things are going to be finite. Well, unfortunately, there's a typo. I should fix this. Let's see if I can fix this here. How do I fix the, anyway, so this needs to be infinity. I'm struggling a little bit about how to actually do the, my buttons don't seem to be working, but okay. Anyway, so this quantity, F internal, should go to infinity, basically. Um, does that make sense? Because acceleration of the individual object goes to infinity, that really means that the internal forces are going to infinity in this limit of delta t going to 0. Okay, so that's a chain of reasoning. Sort of realistically, in typical collisions, F internal is just large. The two objects come together, there's a large interaction force, but in our idealization or simplification, where we say delta t goes to 0, that internal force is not just large, but goes to infinity as delta t goes to 0. Of course, in reality, F internal is just large, not infinity, because there's no such thing as infinity. Nothing, well, nothing that we can see and measure can go to infinity. But in any case, but in this limit, F internal goes to infinity. Any questions about that? So what we've done so far is to basically show the external forces, whatever they may be, have no impact, so to speak, no impulse, so have no effect on the momentum. And all the momentum change is accomplished by these internal forces, which are doing basically finite momentum change in infinitesimal time, having basically an infinite force. The impulse of this F internal is basically integral of F internal dt. And that's of course equal to m2 v2 final minus m2 v2 initial. Impulse equals change in momentum. Now we are applying it to just m2, right? So if you look at this integral, basically it has the form of infinite force over infinitesimal time. It kind of has the infinity times 0 form. If you recall your calculus stuff, this is an indeterminate form. But in this particular case, it so happens that this infinite force integrated over an infinitesimal time results in this finite change in momentum. Yeah, I guess that's that. Any questions about that? Right, so collisions in this limit can be described as infinite forces acting over infinitesimal time to produce a finite change in velocities of the various objects. Or more realistically, it's large internal forces pushing the objects apart over a very small amount of time, so the velocities change substantially over a small amount of time. Any questions? I guess let's see if there's a question. Yes, so yes, it's a very large force in a very short amount of time that gives a finite impulse. Yeah, in this case, yeah. Or in the limit, it gives you infinite force over an infinitesimal time, gives this finite impulse. That's right. Cool. Okay. So the next question. So that's sort of what happens during the collision in terms of forces and velocities. We can also talk about, and then about momentum. We can also talk about mechanical energy, whether that's conserved or not in a collision. What would our guesses be? Is mechanical energy conserved in the collision? Any answers? I guess there's no chat window. Since velocity changes, no, various folks are saying no, ideally they would change. Ian says depends on whether elastic or inelastic. And the answer is basically all of those things. Um, well, it turns out that the velocities can change without the energy changing. But basically, typically, velocities change in a manner that there is some change in mechanical energy. And then, as Ian said, there's a very special case called the elastic collision where energy does not change. But typical situation is that energy does change. So we'll come to that. Okay, so the answer to this question is not generally. Collisions usually, well, I should say, well, may, of course, but collisions usually have delta mechanical energy not equal to zero, usually less than zero. So change in mechanical energy less than zero, which means that final mechanical energy is less than initial mechanical energy. In other words, there's loss of mechanical energy, LOSS, right? And I was going to ask this question, but I guess I put this up on the screen already. Where does this mechanical energy go? Well, when two objects collide, there is some sound. Sound is energy. So some of that mechanical energy gets converted to sound. When two objects collide, sometimes those objects break. The breaking or damage of an object is basically breaking bonds, internal bonds, and the chemical bonds and the object apart. That takes energy. So some of the mechanical energy gets converted to basically creating this damage, breaking those chemical bonds or mechanical bonds. Sometimes it gets converted into heat. And the rest remains as macroscopic kinetic energy that we see as velocity. Okay. Any questions about that? So usually when there's a collision, mechanical energy goes down, and the amount by which it goes down is converted into heat, sound, mechanical damage, maybe light in some cases. Yeah. Do we know what heat is? What is heat? I don't know if you guys learned about it in physics. The word heat is related to one of the quantities that's on this page. That's right, movement of particles, mechanical energy of particles. What we mean by that is actually more specifically, if you have an object, if you have an object like this, let's say, and it's moving in some direction as a whole, that this m1 times v1 square divided by half is the macroscopic kinetic energy of this object. But this object has sort of individual atoms and molecules, and the object as a whole moves with some velocity, and half mv squared is the kinetic energy of the whole object. But it turns out that if you strike an object, the internal atoms and molecules move relative to each other. So that there is kinetic energy there, which is not accounted for by this macroscopic movement of the whole object. And that internal kinetic energy of those atoms and molecules vibrating is actually what we call heat. Heat is nothing but the internal kinetic energy of these atoms and molecules. Okay, so basically, two objects come together, collide. The sort of macroscopic velocity of these objects gets converted into microscopic motion of internal motion of the atoms and molecules, which we call heat. And that vibration sometimes gets propagated into the air. sort of sets up vibrations in air, which we hear as sound. And then, of course, sometimes we break those bonds to cause mechanical damage. So everything kind of is mechanical, but doesn't count in the in what we have so far called kinetic energy, I guess, which is half mv squared, which is the macroscopic velocity. Okay, in some sense, heat is a kind of kinetic energy, but of internal atoms or the component atoms. And sound energy is kind of a kinetic energy because it has to do with kinetic energy of moving air particles. Mechanical damage, I guess, is not kinetic energy. It's just like bonds broken. Okay, makes sense? Okay, that's about collisions. And then explosions are kind of like reverse collisions, where you have internal chemical energy or nuclear energy, as the case may be, gets converted somehow to macroscopic kinetic energy. So it could be that initially the object is just sitting still, has no kinetic energy, and then someone lets a fuse or something, and the thing explodes. The chemical energy gets converted into macroscopic kinetic energy. And of course, there may be heat and so on, heat, light, and so on as well. But objects objects previously that were not moving are now moving. So that's the kinetic energy. So it's as if kinetic energy got generated. So here, mechanical energy goes down in collisions. In explosions, often mechanical energy goes up from before to after. Any questions? Okay. And then, like Ian mentioned, going back to collisions, there's a couple of different kinds of collisions. Elastic collision, which is a very, 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 very special case where mechanical energy change, when we say delta, we mean change, is exactly equal to 0. And then, so that's a very special case. It never really happens in reality. The typical case is mechanical energy goes down ever so slightly. All these special cases never happen in reality, but sometimes it's a good special case to think about because there are some collisions that are close to elastic. And sometimes thinking about that limit gives us some intuition that does not necessarily require considering all the details of things. Okay, so even though elastic collisions are unrealistic, they don't happen in reality, we like to study them because it's a simple special case that builds intuition. And some collisions are close to elastic, if not exactly elastic. Okay, so that's mechanical energy equal to 0. I want to say I'm sort of using kinetic energy and mechanical energy interchangeably here. And why is that? I just revealed the answer, but can someone say sort of why am I using mechanical energy and kinetic energy interchangeably? What happened to potential energy, like gravitational potential energy or spring potential energy? Yeah, so exactly. So someone said this on the chat window, Rowan said it. It's kind of like momentum. Basically, potential energy usually happens to do with change in position, right? So if you take gravitational potential energy, it has to do with the height of the mass. And over a very short period of time, the velocity changes in a collision, but the velocity is still finite, right? The velocity, the force is going to infinity, internal forces, but the velocity goes from one finite number to another finite number. I don't know, maybe it goes at 2 meters per second, maybe it goes to 1 meter per second, right? So the velocity remains finite. And if the velocity remains finite, even though it changes over a very, 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 very short period of time, that finite velocity doesn't change the position, right? It changes the position basically infinitesimally. And because it changes the position infinitesimally, the potential energy change is basically 0, right? So that's why when we say mechanical energy for collisions, with delta t going to 0, the change in mechanical energy is basically kinetic energy, because change in potential energy is 0. There is no change in position effectively because there's not enough time for a change in position. So basically, there's no change in potential energy. Any questions about that? So velocity changes, but during its change, it remains finite. So over a short period of time, that finite velocity, you cannot do anything in infinitesimal time. Okay, so we can use mechanical energy and kinetic energy interchangeably, because all the things that we call potential energy requires a change in position to actually take effect. Okay, so moving further, elastic collisions, delta mechanical energy equal to 0, or equivalently delta kinetic energy equal to 0. And then we call something inelastic. Inelastic means delta kinetic energy less than 0, some lost energy, some lost kinetic energy. And like we said, all collisions in the real world are inelastic. And then elastic is a very special case, idealization. And then there is a limit of inelastic, which is called plastic collision or perfectly inelastic collision, which is the sort of the other extreme. This other extreme is actually when the two particles come together, and after the collision, they basically get stuck together. They have the same velocity after the collision, right? So if you go back up here, the two objects come together, and then if after the collision, V1 final equals V2 final, in other words, they're moving the same velocity in the same direction, that is called a perfectly inelastic or plastic collision. It is a special limit because I didn't write it out here. It's a special limit because it turns out, given the constraints of mechanics, this collision is the maximum energy you can lose in a collision. So this is kind of the worst possible collision in terms of loss of energy. When the two particles come together and get stuck together and move together, is the maximum energy you can lose. Any questions about that? So this is something we can prove mathematically, but we are not going to do that. Yeah, so plastic collisions. So it's not that the two particles come to rest, right? So unfortunately, the two particles cannot come to rest completely unless in some special cases, because the system needs to satisfy momentum conservation, right? So we said the momentum is conserved. So unless you start out with 0 momentum, the final sort of velocities of both objects cannot be 0 because, well, you need to conserve momentum. So if they started out with some initial momentum, the final momentum should be non-zero. And the final momentum being non-zero means that, well, they need to have some velocity. But if the velocities are the same, then it turns out that's the worst case scenario in terms of loss of energy. That's called a plastic collision or perfectly elastic collision. Any questions? Okay, so I'm going to switch as usual to my next PDF here. So inelastic collisions, max amount of energy lost is what we call plastic collision or perfectly inelastic collisions. And then it turns out for at least these particle collisions, there's a simple way to think about these particle collisions using this quantity called the coefficient of restitution for particle collisions. E equals 1 is what is called elastic collision. E equals 0 is what is called plastic or perfectly inelastic collision. And E between the two limits is this inelastic collision intermediate, right? Elastic collision, E equals 1. Perfectly inelastic or plastic is E equal to 0. Just regular inelastic is between 0 and 1, where there is some loss of energy, but not as much as possible. No loss of energy, some loss of energy, E equal to 0, as much energy as one could possibly use. Any questions? Okay. So you can imagine, well, what is the definition of coefficient of restitution? It turns out this is the definition. If you have the two objects moving in the same straight line, in other words, it's a what you call a essentially a linear collision along the same straight line, then E is defined as VA minus VB final divided by VA minus VB initial with a negative sign. Okay. Does this remind you of something, the numerator and the denominator, for the definition of coefficient of restitution? What's the numerator? Is there a term that we have used for this numerator or the denominator?
The velocity of A with respect to B.
Exactly, right. So it's just the relative velocity, right? So this is the velocity of A with respect to B. This is basically the velocity of B with respect to A, or negative of the velocity of A with respect to B. So in the denominator, you have the initial relative velocity. In the numerator, you have the final relative velocity with a negative sign, okay? It turns out you can sort of say this in a more intuitive way. In the denominator is basically the approach velocity, like the velocity with which the two objects are approaching, assuming VA minus VB is positive, I guess, right? And then if the denominator is the approach velocity, the numerator with a negative sign is the velocity with which they go away from each other after the collision. Okay, so if you write it in words, you can write the denominator as velocity with which the two objects approach each other, like the rate at which the two objects are coming together, and the numerator is the rate at which the two objects are going apart. Okay, if they come together at the same rate as they are going apart after the collision, then you have an elastic collision. If not, you have an inelastic collision. Any questions about that? Okay, so it looks like there's a remark or question. Yeah, relative velocity, that's right. Okay, cool. And we can imagine sort of a standard kind of a problem, which is basically using the two principles that we've looked at so far. So imagine a problem like this. Ball A hits ball B going in the same direction. Mass of ball A is given, mass of ball B is given, velocity of A is given, velocity of B is given. And then you're told, hey, the coefficient of restitution could be 1 or 0.5 or 0. How do you solve this problem? You're asked to solve for VA final and VB final, the final velocity of A and final velocity of B. You need, because you have two unknowns, you need two equations. One of the equations is the momentum balance equation, and the other equation is just based on the coefficient of restitution. Initial velocities are known, coefficient of restitution is given, the final velocities are unknown. So you have two unknowns here, and then the momentum equation also has two unknowns. You solve for the two unknowns with the two equations, whatever may be the coefficient of restitution. Any questions about that? So that's pretty straightforward. You'll see like the homework problems basically rely on this equation. So pretty straightforward situation. If coefficient of restitution equals 1 or 0, it turns out that you can still use this equation, but it turns out you can sometimes use a different equation to make your life easier. So if coefficient of restitution equals 0, we have stated that, well, I guess it's pretty clear. If E equal to 0, VA final equals VB final. So E equal to 0 just becomes equivalent to final velocities being equal, which you can plug in here. VA final equals VB final. So V final is just going to be this initial momentum divided by MA plus MB. So pretty straightforward. If E equal to 0, that's kind of the simplest situation. If E equals 1, then you can still use this equation. You can say E equals 1 and then use this equation, manipulate things to solve for the velocities. Alternatively, you can say half mv square for the two masses initial total equals half mv square kinetic energy final. So instead of saying E equals 1, you can also use kinetic energy initial equals kinetic energy final as an alternative equation, but I do not actually recommend it. If you're told elastic collision, just use E equal to 0, because the kinetic energy equality is like a quadratic equation, like we have all these V squares. Much better to use just E equals 1, so you have VA final minus VB final equals something about the difference in the initial velocities.